Okay, so before we wrote the test, we were talking about banked curves and unbanked curves. Okay? Remember that in a banked curve, it's the angle of bank giving us some normal force that provides the centripetal force to keep you in the corner. For an unbanked corner, it is friction that holds you in the corner. Okay, so I want to see if you can remember how to do an unbanked corner question with this one here. So write this one down and give it a try. Okay, let's see how you do, and then we'll walk through it in a few minutes. Okay, what acts as a centripetal force for an unbanked corner? Yep. Okay, so force of friction is then acting as our centripetal force. Okay, that's kind of our first thing. We know the mass of the car, and we know the radius of the corner, and we know the coefficient of friction. So if I'm setting this up, I'm going to have mu times the normal force equals mv squared over r. Okay, that means mu times the force of gravity equals mv squared over r, because this is an unbanked corner where normal force and gravity are equal. Everyone all right with that? Okay, what can I do with mass?
No math.
Yeah, I can cancel it. It's on both sides. When I start manipulating, mass is going to cancel anyway. Okay, so I'm going to get rid of it right now. And I'm going to look for the maximum speed. So I'm looking for v. So I'm going to multiply both sides by r. That's going to get me v squared. I want v, so I'm going to take the square root of that. Okay, and I'm going to get that v is the square root of mu. Okay, that's going to be, what was it, 0.6? So 0.6 times 9.81, and the radius of the corner was 40 meters. So square root of 0.6 times 9.81 times 40. All right, so the maximum speed on that corner is 15 meters per second. Okay, everybody all right with that? Okay. Yep.
How come you wouldn't use the one formula has v equals 2 pi r over t?
Because I don't have t.
Can't you calculate 1 over the force?
I'm not sure.
No, that's 1 over frequency.
Frequency, not friction, but okay.
Does that make sense?
Yeah.
Yeah. All right. So let's have you guys try 1 and 2. Okay, so they're all unbanked corners. Let's have you guys try 1 and 2. All right. So on question number 1, so we've got an Edmonton oiler with a mass of 100 kilograms carves a turn with a radius of 7.17. So we know the mass, and we know the radius, 7.17 meters. Okay, before he feels his skates begin to slip on the ice, which means he's right at the maximum static friction of that corner. Okay, we're looking for the coefficient of we're looking for his speed. So it's basically the same calculation we just did. We're going to have mu times m times g for our force of friction equals mv squared over r. Okay, m is going to cancel. V is going to be manipulated to be Muger, square root of Muger. Okay, and so that will be 0.8 times 9.81 times 7.17. Okay, which will give us a speed all right, 7.5 meters per second. Okay, how are we doing on number 2?
What's the conversion of 90 watt
Divide by 3.6. Okay, we need a couple more minutes on number 2.
Give it one more minute.
Okay, let's have a look at the second one here. So this is exactly the test we were talking about when we talked about unbanked corners, okay? Testing the handling ability of a new car design. So we know that the radius is 100 meters, okay? We know that the maximum speed is 95 kilometers per hour, which we need in meters per second. So that'll be 26.38. Okay, and we know the mass is 1,200 kilograms. Okay, so we're looking for mu. So since it's an unbanked corner, force of friction equals our centripetal force. Okay, and so that's going to be mu times m times g equals mv squared over r. If I'm looking for mu, my m's are going to cancel. Then divide both sides by g, and I'll be left with mu equals v squared over rg, which I pointed out last week is also the same as when you're calculating the tan of theta for a bank curve. Okay? Any curve is dependent on the same three things: speed, radius, and gravity. Okay? So mu then is going to equal 26.38 squared divided by 100 times 9.81. So that number squared divided by 981. 710. 7.710 as our coefficient of friction.
How do you get kilometers per hour into meters per second?
Divided by 3.6.
Okay.
Okay, did we not remember how to do that in unit 1?
I don't remember.
Yeah, I'm pretty sure I
I
did,
think
but
we
let's
did,
just
but-
quickly review here. Okay, so if I've got something in kilometers per hour, and I want to go to meters per second, I've got to do what's called a compound conversion, right? That means I've got to convert the kilometers to meters. In 1 kilometer, there are 1,000 meters, right? So I've multiplied kilometers by 1,000, and that'll get me meters. Everyone okay with that? Okay, and I've got to convert the hours to seconds. In 1 hour, there are 3,600 seconds. So really what I'm doing is I'm taking kilometers per hour and multiplying by 1,000 and then dividing by 3,600. Well, that's the same as taking kilometers per hour and multiplying by 1 and then dividing by 3.6. That's why I say just take kilometers per hour and divide it by 3.6, and you've got your meters per second. And if you need to go the other way, you multiply. Yeah. One bank curve quick. Where's my bank curve quick? One bank. Where are they all unbanked? Where's my bank? There we go. There's bank curve. Try that one. Bank curve question. Okay, so in this question here, we're told the radius, 125 meters, okay? We're told that it's angled at 20 degrees, okay? And that we're looking for the maximum speed, okay? Well, our bank curve formula is that the tan of theta equals v squared over r times g. So all we're doing is manipulating for v, okay? So that's going to be the tan of theta times r times g square rooted to give me v. Okay, so that'll be the tan of 20 times 125 times 9.81, okay, and that should give us 21.1 meters per second. Okay? All right, tomorrow we're going to be doing a lab on speed and radius. Okay, it's pretty straightforward, okay, but that's what we're gonna be doing tomorrow. No, we're not using the carts for this one. Rubber stopper on a string
Okay.
and a piece of PVC tubing.